Hello, welcome into the video here. It's been a little bit of time since I finished the last video, so apologies for any seemingly discontinuities from where we left off in what was video 6 and into the 7th video on the series of the investigations into the NACA 0009 airfoil for a front wing application on a STEM racing competition car. At the end of the last video, if memory serves me correct, I had stopped the calculation after what looks to be roughly 215, 216, 17 iterations, having seen here that the equations being solved by the iterative solver, by the fluent solver, had converged to a reasonable level. Continuity never seems to come down the same level there that everything else does, but for that matter, everything else has come down to a nice iterative error or numerical error on this. So our next step is to post-process effectively, or to look at the solutions. Now, in the workbench itself, a couple of ways we can evaluate the solution. We can update the solution here now, which we will do whenever we click into solutions to look at contours, or we look at XY plots and whatnot. But what you also will have, there's a results file here as well. And a lot of times what we can do is we can drag the solution into the results and do post-processing in that. Now, I don't particularly, I don't have any particular fondness for that results component. And I prefer to do the post-processing or the evaluations in the solution itself. Now, which can be done, I find. So what is it that we're going to look at? So we have our scaled residuals, everything looks good there. We can still see the mesh was running in a window to the back. But what I typically look at first, and what most people I think would, or with my own experience, would be in the graphics side here to look into the contours. So if I double click onto the contours here, and what a lot will look at here maybe is the pressure contour itself. So in the pressure contour, you need to do, it is defaulted when you open up the contour. You can rename it here if you want, which I might just do that. Let me just put that as pressure contour. I've never found any need to specify that as the static pressure contour as opposed to dynamic pressure, any other type of pressure contour, and that it's usually the static contour that I have looked at. And save and display, and that'll bring us up the contour. So on the outset and at the scale, it looks to be a fairly uniform pressure in the flow field, and that of course is the case until we zoom in and we see the surface there that's exerting a dynamic influence on the flow around it. So what we see here is the NACA 0009 airfoil profile in it, and we see its effect on airflow around it with respect to pressure. All right. So we see in here, for the most part, according to this, we are apparent to be, let me get them there to scale up. Let's see here, just get her up a wee bit this road. Get that up there, and see if I can just drag this out a wee bit more. And then let's see if we can pull that over. Yeah, so this kind of sky bluish color out here seems to be in around maybe about 30 Pascal or that, according to that. Whereas when we start getting into the airfoil, we see this region here where pressure is building till it seems to hit a maximum point to a very deep red, very deep scarlet there, right at the leading edge of the airfoil. And that's indicative of what we would expect. So you can imagine air particles ploughing into the front of this airfoil as they approach it and eventually hit it at 29 meters per second. And we're obviously going to have a we wouldn't really call it a stagnation point as such, not so much, but just hitting it there and then kind of trying to make their way back, being driven back, and then hitting more air coming in, and that's where the pack and the pressure is building up. No danger of Mach numbers or approaching any sort of critical Mach numbers here. The velocities are still far too low to have any sort of effects with respect to Mach, but certainly we can create a field variable for the flow and display that for Mach contour. Now, the one thing I will say about that, if you did have an interest in that, maybe in more high high Reynolds number flows is that because we have chosen a pressure-based solver here as opposed to a density-based solver, the Mach number, the Mach contours don't naturally come up on your contour plots when you're looking to plot it here, contours of. We won't get it there. But when we are using a pressure-based solver, it's very easy to make a named expression for a Mach number. And all we'll do is we'll just write an expression there for what the velocity is, the velocity magnitude. Of course, as a field vector, it'll be velocity vectors and what their magnitude is at each cell center, divided up by the local value for the speed of sound. And then we can display that on a contour plot if we so want. But that's really not of any major concern with respect to stem racing, so we'll leave that. But yep, if you want to see that happen, let me know and I'll be more than happy to do it. It will literally only take about 3 minutes. So after that high pressure region, we could see a darker region, a more royal blue color above and below. And again, importantly, I can see kind of a symmetric distribution of that contour, which would be expected for a symmetric airfoil with a zero angle of attack. We should be getting the same effect happening above the airfoil as below the airfoil. And with this darker blue region relative to the blue regions on the kind of more far field areas indicates is that I have a lower pressure over here. Moving back towards the back of the airfoil, I could see that the pressure slowly started building as they go more sky blue, and then there is a particularly noticeable greening of the flow field here. Not immediately after the airfoil, but a little bit downstream of it, where I can imagine slipstreams coming from the top and the bottom, meeting again, and a little bit of squeezing happening there, which would raise the pressure slightly. But that's only a guess until we give this some further analysis. Right? So some of the further analysis that might reveal some insight into what's going on is also to look at the velocity contours and that. So I could have just selected velocity and velocity magnitude on that contour plot and overwrite that, but what I'm going to do is I'm going to right click, I'm going to create a brand new one here, and I'll call this one velocity contour, like so. And this time the contours I want to inspect are going to be velocity. And what is about velocity? But velocity magnitude. I'm going to select the fluid flow field here. Again, you don't have to, but I would normally always select the fluid flow field. These will display if your boundary conditions, my standard ones here, the inlet, the outlet, and the wall. And I think with the sys on it there, where flow field happens, you'll not see much. But fluid, you don't have to select it. I always do. Force a habit. Save display. And voila, there's our velocity contour. So what we can see out here is a kind of a tomato color with a broadly red but a maybe tinge of orange in it for the vast majority of the flow field, particularly out in the far flow field, which is indicative, again, if I can just zip this up and bring that down, in and around the 29 meters per second mark is what I would expect, because again that is my my specified inlet velocity. However, as I come closer into the airfoil, again top and bottom becomes a much deeper red, and that is indicating higher velocities here. So going by this scale, I can see my peak velocities occurring in here at a roughly 32.9 meters per second. So despite 29 meters per second coming in at the inlet, I have an accelerated flow in places there where I have the darker reds, which is going to happen right at the very tip of the boundary layer, at the thickness of the boundary layer, at about 99% of it. I'll see a very high speed. I'm coming, well, maybe up a wee bit off it there, but that's where my high speed is going to be bounded on. But what that is, that's coincident. We can see an inverse sort of relationship where we have high speed versus low pressure. And down here, where I come to a stagnation point on the blue, which is 0 meters per second, that's also coincided where I had the highest point of pressure. So we seem to be seesawing in some way between velocity and pressure, and that is true. That is what we'd be expecting to see, and that there is, broadly describes the Bernoulli effect, which is the that your pressure is a constant, but it is made up of components. Pressure being, broadly speaking, the amount of energy in a volume or in a space, not strictly defined like that, but you can imagine it like that. And that's either going to be made up of where we take gravity effects out of it, and internal pressure effects maybe, the potentials, the squeeziness of it, as well then as the kinetic energy of it, the kinetic, the dynamic pressures. So we could see here where we speed up and our kinetic energy rises, our potential energy in our pressure drops, and vice versa here where we lose speed. We will again see that our here at the nose, our pressure rises. Okay, and that's what gives the airfoil indeed a component of what makes it either produce, what's that onto velocity? Oh, say display. There we go. That effect there of the accelerated flow producing the lower pressure is part of what gives the airfoil its ability to apply I suppose the fluid to imply on the airfoil a force which is perpendicular to the direction of flow, which will be in this case in two dimensions, up or down, depending on the symmetry of the airfoil, the camber, and the angle of attack. But here again, symmetric airfoil, no angle of attack. What we see in the top is what we see in the bottom. So the airfoil, for want of a better description, should really be floating between, in this case here, two high accelerating flow regions, or if you prefer, we should see it there, pressure contour, floating there between two low pressure regions. All right. Now, it's important there as well. I think it's, if you ever quiz on it, I don't think you ever will be as such, but just that you'll often hear there that it is this negative pressure that gives lift. Indeed, if the airfoil is so orientated to give lift, or it's that low pressure here that gives downforce if indeed the airfoil is inverted and orientated to give downforce. But that's not strictly true. That's only part of the story. I think it's widely enough accepted that indeed the pressure differential across the top surface and lower surface of the airfoil, that pressure differential there does act on the airfoil surface, and it does lift the surface. Well, it doesn't really lift it. It allows the airfoil to be pushed from the high pressure into the low pressure region, and that does give an element of the lift. But there's also, it can't be forgotten, the classical mechanical element there of it as well, the Newtonian effect, which is the momentum shift there, the transfer of momentum, which will generally be given by the angle of attack there, which will lift up the airfoil, which also has the effect of being responsible for part of the lift. So with all that said, we can also see here very interestingly, see, why did you make that 20 chord lengths out to the back? We'll have a look. The not so much the wake, I wouldn't even call it a wake that far back, but certainly a slipstream coming off of that. It reaches very far back, 29 meters a second. It's not massively fast, but still, like what we're looking back there, is half a meter past a 25 millimeter, 1 inch long wing, half a meter away. Its effect never be perceived really by us at our scales, but certainly can be witnessed. So that there is our velocity and our pressure contours, and they are very much like what we'd what we'd expect. What I would say as well, especially when we're looking here at the velocity, something that's always worth noting and making sure that you're fully aware of, and if it makes sense, let the judges know you're aware of it, is the boundary layer. So the boundary layer in itself is the area of the flow close to the surface in which viscous effects have an influence in part. So we can broadly ignore the facts or the influence of viscosity out here, or any sort of shears out there, but definitely within this region we can't. And what we could see right pinned up to the surface here is this blue region which abuts the surface, and that translates back into 0 meters per second, which gives evidence there of a no slip condition, that at the surface that laminate of air effectively is stuck to the surface and it's gripping it. It doesn't want to let it go. That's drag. Right? So that's friction drag on that. And that's one component there that's going to slow us up. And for that reason, the longer this top surface is, the longer the bottom surface is, the longer the surface is, the more drag you're going to get. And for that reason, we don't want the plan form of this airfoil, which I mean the bird's eye view looking down on it. You don't want that too big. The bigger that is, the more drag you're going to have. Drag is, in our case here, the enemy. So that's one element of the drag, is what you can see on this increasing boundary layer. It starts off very thin, and as we move to the back, you can see that kind of yellowy, orangey region gets more and more orange, more and more orange. Yellow gets thicker, sky blue gets thicker. That's the boundary layer. It's increasing. Right? So the longer that goes, the more friction you're getting, and the more the effect of the friction you get. And remarkably enough, on this NACA 0009 airfoil, there's no huge, it's sticking to the airfoil very well, which I will say is, I think, is odd. If you looked at an NACA 0012 airfoil, especially at 50,000 Reynolds numbers, there's papers been written on it of the laminar separation bubbles, where you'll start to see the flow separating from the airfoil at various chord lengths, or at various normalized chord lengths, and before reattaching again. When they pick up a wee bit of energy from the free stream, they come back down, and again, in some worst case scenarios, they don't reattach at all, and the separation bubble, of course, that bursts and causes a stall, which is a massive drag effect. But anyway, them bubbles appear on here. It's just like adding a bump onto the airfoil and taking away, putting another part of the airfoil into the free stream or into the flow, causes more drag. So yeah, what I will say is we have a very pointy edge here as well, which wouldn't be indicative of a true airfoil. So if we had a more rounded edge, we mightn't get such a long stream out of that. But it's something there to look at. But your boundary layer there, you can see, is starting to come away from it here. Obviously, there's nothing more to stick to. And the two flows are convergent, which corresponds there to that little section of the higher pressure, that squeezing that we've seen in the pressure contour. Okay, so I think that's enough said there about really the velocity and the pressure contours, but you can surely see that there's whole points of discussions. You could talk for hours about it, and I haven't even looked at the likes of the path lines and our streamlines in this. So what are other things that we'd want to look at in here? Well, we went to the effort of creating a couple of report definitions, the drag coefficient and the lift coefficient on this as well. And the reason for that there is that the drag coefficient and lift coefficient, it'll allow us to calculate drag forces and lift forces, or negative lift forces as it may be, to apply to the physics or some sort of a model of how your stem racing car might go down this track. You'll need to know what your deceleration rate due to drag is going to be. But it also allows us to validate our results to a level of confidence in that the drag coefficient and lift coefficient is usually what results our CFD results are measured against, because that's what's measured in experiment for an airfoil. So if I look at and by the way, the lift coefficient here, I'd expect to be 0. Why? Because look, the pressure seems to be equated top and bottom for the most part, which I should have a neutral buoyancy really in it. And as well as that, that's the velocity top and bottom. The pressure, as we've seen, should be the same top and bottom. So, it should be there. It'd be very unlikely that we'll get a full 0 on this, for the simple reason here is that, when we run this into CFD, we'll have inherent errors, whether it be the numerical error itself. It will also have errors there to do with the discretization as well, and we'll also have the errors there that are going to be associated with rounding off numbers, kind of our machine error on this. So there's a few different errors there that are going to creep in, or which are going to result in metrics and values that aren't necessarily what we'd experience in real life. But however, let's get a look at what we have. So if I go to lift coefficient here, I should see something around 0. And I hit compute down here, print it out. What I do see, it's very hard to see it there now right enough, but it is a negative number. It's not a 0 number, as I didn't expect. So if anything, I have a wee bit of downforce. But it is minus 2.767025 e to the power minus 5, which is very close to 0. Is what I would expect. It is giving me downforce. So from in the spirit of racing, I could say, yeah, I got a result here. I have a wee bit of downforce, even though I'm at no angle of attack and I have no camber. However, if anything, if this was something I could go on, I'd want a wee bit of lift on this, because I'm going down a straight track here. My biggest enemies, especially in the coasting phase of this track, is going to be air resistance and rolling resistance. If I can lift the car off the track slightly, bearing in mind that it's tethered down, I could maybe reduce the effect of the rolling resistance, reduce my resistance somehow by just lifting the car slightly, making it a wee bit lighter and that. So if anything on this one here, I'm not saying you should do it, because it's not really in the spirit of what you're trying to achieve here. You want to keep the car on the track and achieve some level of downforce. All the same, up-down neutrality could be maybe the most, the fairest thing that you could try to achieve for this for yourself. So anyway, yeah, I'm nearly at 0 for the lift. And if I went to the drag coefficient, I should see a drag, because indeed I do. I have a pressure drag here at the front. If I looked at the pressure itself, again, we'd see the high pressure region here, but I'll also have this drag here, these viscous effects. This is all pulling the airfoil back. It's preventing the airfoil from running further to the left, if you like. So when I run a compute on that, I should see a value. Indeed I do. It's 0.0158. Now, this is where I can now go into experimental data, and I can try to find out what other people have found, or what experiments have found, or what other people have calculated or carried out CFD evaluations have got, and have they corroborated their results against experimental data. So within the airfoils here, what I'm going to do is I'm going to look at Winslow's paper. Winslow did carry out evaluations on the NACA 0009 airfoil at low Reynolds numbers, which is, as we can see here, between 10,000 and 100,000. We are firmly between the two of them at 50,000. So if I zip on down to the results, this is some bits there that he has in results. There's pressure coefficient. I can check that, and I will. I'll come back to that one. There's the Mach contours as well. Intermittency, so that's kind of the turbulence breaking in. But here, figure 5, lift and drag comparison of turns 2D, which is their test, with experiments. Experiments for the NACA 0009 at Reynolds number 50,000, which is identical to what we have. So the experimental data is quoted here from Lutz et al. And I have that paper as well. So experimental data is the dots, right? And this is the angle of attack along the x-axis. I'm at a 0 angle of attack. Experimental data shows a slight coefficient of lift here. It's not 0.0. The experimental data is run up above that, maybe at about 0.0 or 0.01, and around there, 0.01, 0.015 maybe. Seems to be what that's got lift wise. The model that Winslow et al. Carried out shows lift of roughly about 0, which is the ideal answer for that, but experimentally it's shown a wee bit of lift. Lift on a horizontal or an airfoil with 0 angle of attack, we're really only going to be looking at magnitude, because it could equally go to lift as downforce on that. So that would state there that even if this dot was down this side here, it wouldn't make any sort of difference. The fact would still be the same, in that we have an imbalance, obviously, of pressure over the two sides of the airfoil. It doesn't matter which side it is because it is symmetrical. But however, that broadly agrees with what we have. We have a very near zero answer to that. So over here, I have a lift coefficient again. That's lift coefficient against angle of attack. It's lift coefficient against drag. But let's see what we have here. If I know my lift coefficient is roughly 0. And for that, if experiments is right, I should be getting down to here, I should be getting a drag coefficient of, that's 0.4, that's 0.2, so that space is 0.02, half that space is 0.01, so that's 0.01, 0.02. I should be getting roughly 0.015 if I can match the experiment. And going back into Fluent, indeed, that's what I have, is 0.015, 158. So I'm just slightly closer to the 0.02 than the 0.015. And that's what that looks like. It looks like our drag coefficient is right on the money with experimental data, if indeed our lift coefficient can be assumed to be 0. But yeah, that's pretty good. So I'm happy enough that looks good. But what I will do, just to make sure that I've checked everything I can, we'll look at the pressure coefficient. So let's get the proper trace. Proper plot is in the blue circle, is the experimental data at angle of attack is equal to 0 degrees, which is this one here. So that's our pressure coefficient. And that there is against the non-dimensional chord length. So the chord is normalized to a distance of 1. And this is the shape we're looking for. So the peak on this one here seems to be roughly at about minus 0.3, minus 0.3, roughly. Minus 0.28, minus 0.3 is what the peak is. And that is occurring at roughly, let me say, about 0.1% of the chord length. So in our case, that should be happening about 2.5 millimeters. We should be getting minus 0.3 if we're right. Now, it's not a field variable. The pressure coefficient, it's not a field variable, so we won't do it in a contour. And this will be done on a plot with an XY plot. And what we're going to call this one here is going to be pressure coefficient. And because it's an XY plot, I'm going to have to specify location along a wall. So pressure, not static pressure, but pressure coefficient. The directional vector, where along the wall. Save and plot that. So there it is there. So automatically this looks to be like it is inverted. But yeah, that's only, I want to say a chord, because if you look here on ANSYS, there's 0, and as I go down I move into the negative numbers, as is normal, as is expected. As I go up I move positive. However, if I look at Winslow, when I start at 0, the negative numbers are running up, so it's just inverted. So the magnitude, I'm going to look at the magnitudes in the negative direction. The magnitude in the negative direction is shown. The negative direction is shown up the way is here, and I'm at roughly, I think, minus 0.3. The negative direction is shown down, and this is minus 2 to the power of minus 1, was minus 0.2 there, minus 0.4 there, and look at that, there's minus 0.3. And right nearly smack bang on what experimental data has. Now, I know it's at, this should be at 2.5 mil, because in Winslow's paper that was being shown at 0.1, or 10% of the chord length. 10% of my chord length is 2.5. Don't think I'm way off, because 0 is running here. can just get onto that scale there. Right, there's 2.4. And don't get that's in meters. 2.4. So I'm right on the money with what Winslow, or not even what Winslow, but what the experimental data shows, and what Winslow's own test that's shown here, this Torrance 2D test, has also shown, which broadly traced that as well. So everything is looking very positive for us as far as that goes. Now we're 30 minutes in, so what I want to do, I might just take one more check at another paper. Sedana, he looks at an NACA 0012, as does Ataki. Lutz also has a NACA 0009 for low Reynolds numbers testing. And we'll zip on down normal operation. Things you can go straight down to the results on these, but sometimes there does be graphs and plots. There's an RG15 scattered through the data that has information we're looking for. There's NACA 0009, original angles of attack 0.35. There's an angle of attack at 0. That's showing a coefficient of pressure. That's the solid black line. Is that, which is probably this one here. And again, look, that's coming in roughly minus 0.3. Okay, so that looks good. That also comes up. Let's just check what that test data is as well. This one here is the NACA 0009 angles of attack of minus. They don't apply to us because we don't have that angle of attack. So anything else? This here, sharp origin. There's angle of attack there of 0. This is measuring coefficient of lift, which we know that 0 angle of attack, 0 coefficient of lift roughly. And yeah, that's fine. Let's drag polars. Conclusion outlook. Yeah, that's it. There's nothing really else on that one telling us much difference. We have that coefficient of pressure. X over C. There's nothing else comparable, I don't think, anywhere. There's a nice one there, CL by CD. That's we could plot that, a CL versus a CD. Even though what we'll be looking at that, maybe it's just one scalar value, a CL over CD, sharp and mediums. I might do that in the next. I'll do CL over CD just now, how to write the named expression and to calculate the CL over CD in this one, and then we'll stop the video and move on to the next one, where we'll set up a couple of other field variables, named expressions, and put in a few functions into this to help us populate a parameter table from which to run our mesh independent study. So let me just X out of that, and what I'm going to do in here is report. I can write in a report definition. I want to put in a variable that isn't just here just yet, but what I'm going to do is I'm going to put it in as a named expression. So I can right click onto that and hit new, or double click into it and click new. And what I want to do here is a variable called L over D, which is lift over drag, and my definition of that is going to be the lift coefficient divided by the drag coefficient, or indeed the lift force divided by the drag force, whichever. The lift and the drag were report definitions. If you recall, we created them ourselves, lift and drag here. So report definitions, I'm going to go my lift coefficient divided by my drag coefficient. Right? So this is going to be my lift over drag ratio. Just be a minus number, because we have a minus lift, but it is, it's a parameter, it's a metric of interest in airfoils, especially if we start varying the angle of attack and we want to plot the performance of the airfoil, various angles of attacks, or even Reynolds numbers. So I will want to look at this without having to come into the solver and run a computation in it. So what I'm going to do is I'm going to tick this here to use this as an output parameter in the same vein as I did that for the drag and the lift coefficient, and hit OK. Alright. So I want to calculate that now. Alright. So if I can double click in the named expression and bring this up in the task pane. If I click that L over D and I run compute, I can see it out here in the console. The L over D is equal to minus 0.0017. So, maybe there's published data on the L over D coefficient. But where you do have pitched airfoils, or you do have cambered airfoils, L over D's, maybe around 38, 39, 40. I don't think are, I think it's a pretty good one. It's not to be corrected on that one, all right. But yeah, that's my L over D now. So I can save that and I can output that to a parameter table. I'm going to X out of that for now. I'm going to X out of Fluent, and I'm going to close the video up with the workpage project, or the workbench project schematic. Clean that there. I'm going to save the settings just for this calculation. The workbench here, since this is the first time I'm back onto the project schematic, since I ran the solver, and you'll see that this parameter set, this other cell has been added. And what that is, because I had ticked for an output parameter on my two report definitions, which was the lift and the force coefficients, as well as for the L over D, I need somewhere to view them parameters or to store them, and this is where they generally happen, in here. Okay, so I'm going to click out them ones there just for now, and here they are here. So unfortunately, I just have to run the solver one more time. I'm probably going to have to stop this because the calculation is not going to complete in an appropriate amount of time. But if I would have updated them, obviously when I restarted this, as I said, it's been a couple of days since my last video, I should have reran the calc and stopped it again just to update all my values. This would have been populated, but I can now add in another design point, and if I had any input values, which I will create in the next video from either named expressions or field functions, I can alter them here, including velocity, angle of attack, whatever I want, run the calculation out here, and that saves me having to go into Fluid, and it will output for me my values. Okay, so for the mesh independence, we'll also look to populate this with maybe mesh sizing or spacings and whatnot. So there's 37 minutes. That's a wee bit of work on the post-processing and the validation. Well, definitely I think we've verified as well our calculations, everything looked good, and that our solver work, we've also validated there against other published data and experimental data that has been published in academic papers and has been replicated by other contributors to the same airfoil, the same Reynolds number, the same angle of attack, using the same solver. So yeah, that's really all we can do with that. So I'll call this video quits, and then we'll come back in the next one and we'll get back into mesh independence. Okay, thanks very much, and thanks for watching.